In this video, we're going to discuss Lewis acids and bases. Before we introduce the new definition of Lewis acids and bases, let's revisit a definition you probably know already, the Bronsted-Lowry acid-base. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Here's a chemical reaction where a proton reacts with ammonia and forms ammonium. Using the Bronsted-Lowry definitions of acid and base, the ammonia is a base because it is a proton acceptor. If something is accepting a positive charge, it could also be thought of as donating a negative charge. So not only is the ammonia a proton acceptor, it could be thought of as an electron donor. As you can imagine from the name, the Lewis acid-base definition is all in the context of electrons, just like the Lewis structure is all based on electrons. So a Lewis base is now an electron donor, and therefore a Lewis acid must be an electron acceptor. Notice that the Lewis and Bronsted-Lowry acid-base definitions are in complete agreement. If something is donating electron density, it could be accepting a positive charge. Let's look at another chemical reaction where boron trifluoride reacts with ammonia to form this Lewis acid-base adduct. This is an acid-base chemical reaction, but we have to use the Lewis definitions of acids and bases. Notice that, again, ammonia has a lone pair. It is donating electron density into the empty p orbital of the boron. So ammonia is acting as a Lewis base because it is donating electron density. The boron trifluoride is acting as a Lewis acid because it is accepting electron density from the nitrogen, or the lone pairs on the nitrogen. The covalent bond that's formed in the Lewis acid-base adduct is interesting because it's called a coordinative covalent bond. Notice that both of the electrons in that covalent bond came from the nitrogen. Typically, we think about covalent bonds being formed where one electron comes from each of the atoms forming the bond. Here's another Lewis acid-base chemical reaction where water, acting as a Lewis base, reacts with carbon dioxide to form carbonic acid. One way to think about Lewis acid-base chemistry is as an umbrella category that encapsulates all of the other acid-base chemistries you may have encountered in the past. Let's start with the most stripped down or simplified form of acid-base chemistry that you may have encountered before. That's an Arrhenius acid. An Arrhenius acid is a proton donor in water, and an Arrhenius base is a hydroxide donor in water. The next category beyond that is Bronsted-Lowry acid-base chemistry. A Bronsted-Lowry acid is a proton donor, and a base is a proton acceptor. Notice that there are lots of Bronsted-Lowry bases that are not included in the Arrhenius base category. For example, ammonia, NH3, is a Bronsted-Lowry base because it accepts a proton, but it would not act as an Arrhenius base because it does not donate hydroxide. The final kind of big umbrella category is Lewis acid-base chemistry, and we just learned that a Lewis acid is an electron acceptor and a Lewis base is an electron donor. The benefit of thinking of acid-base chemistry in the context of electrons is that all molecules have electrons, so we can think of them in electron donor acceptor context, not all molecules will have protons or hydroxide. So the Lewis acid-base chemistry context is much more useful, especially when you move into organic chemistry or other advanced chemistry disciplines.